we're going to kind of start the last thing here. So let me sketch just some random graph. And let's say that I've got some curve. I've kind of drawn like a parabola-y looking thing. And there's some area that's contained between that thing and the x-axis. And where I'm limiting myself to going between x equals a and x equals b. I happen to make those roots here. They don't have to be, but I did just for the sake of the picture. Okay, so that area is something, and we would like to be able to find that area. Um, Now, if the shape is something like a semicircle or a straight line or like a triangle kind of thing, then we could throw all the usual rules from geometry at it to know what that area is. Okay. But if it's some weird random squiggly thing, then how can we figure out what it is? Okay. Huh? Yeah, some kind of calculus, right? That's the whole game here. Okay. So the first thing that we're going to do is make a notation for what this answer or this question that we're asking is. And we're going to notate it like this. Okay, so if we have some function here, let's just say it's f of x, then I've got this s thing that we've used before when we talked about antiderivatives. Okay, but this time I'm going to put the number a and the number b sort of on the bottom and the top of it. And there's also this dx thing, which needs to be there for a reason, and we'll talk about why in a little bit. Um, okay, so that notation is going to mean the signed area between the curve and the x-axis. Okay, now why do I mean signed area? Is because let's take, for example, something like this. And let's say we have a, b, and c. So this is the integral from a to b of f of x dx. And this area would be the integral from b to c of f of x dx. Okay, area cannot be negative in geometry. But we're going to allow this thing that we're talking about, this integral, it can be negative. And there's good reason for that. But basically, how do we know whether or not something's going to be positive or negative? Well, if it's above the x-axis, we'll count it positive, and if it's below the x-axis, we'll count it negative. Okay, that seems logical, right? Okay, now the reason that we want to be able to do this is because to be able to have positive and negative is well, okay, maybe a way to think about it would be like in economics or something. You have positive quantities and negative quantities. So let's say that your costs are $1 million and your revenue is $1 million. Then what's your profit? Zero. Okay. And how did you get that? Well, the revenue counts positive a million, and the costs count negative a million, and those, of course, happen to add up to be zero in that case. But it's totally reasonable to talk about negative quantities. Okay, so even though geometrically the area underneath, sorry, between the curve and the x-axis is always a positive thing because it's an area, we're going to count anything that occurs below the x-axis as negative. Okay, and there's good reason for that, as we'll see later. Okay, um, and so the question is, how do we actually find these things? Well, that actually, as you can imagine, is going to involve a lot of work, unless the function is relatively nice looking. Okay, so let's take a look at this first graph, which is just made up of a bunch of pieces of straight lines that are kind of stuck together. Okay, and let me just kind of make a crude sketch of it for the sake of demonstration here. So we've got 1, 2, 1, 2, 1, 2. So it goes up to here, 2, 3, 4, over to here, then down to here, then down to here, then up to there. Oops. Okay, something like this. Okay, yeah, I know, right? We could. I just need to sign it, frame it. We can put it in the Louvre. Yeah. Okay. So, got all of that. Um, so what's the area that this thing contains? Well, it depends on what piece of it we want to talk about. Okay, so down at the bottom there, we've got four of these integrals. Okay, so we've got 0 to 4, 0 to 6, 4 to 6, and 3 to 8. Okay, so different pieces. So let's take the 0 to 4 case. That would be all of this stuff. Okay, and actually, let me uncolor it and because if I wanted to find the area, what am I going to do? Yeah, I'm going to split it into these two pieces. So because the first piece is a triangle, and that requires one formula, and the second piece is a rectangle, although it's a square in this case, and that will require a different formula. Okay, so here it would be what, 0 to 2 of this is what? So what's the sort of greenish part? Yeah, and how did we get that? Base times height over 2, and we get 2. Okay, and then from 2 to 4, what do we have? Yeah, it's base 2, height 2, and it's a rectangle, so we don't have to do any division, so we get 4. Okay, and so what is from 0 to 4 then? It's 6. It's the sum of those two things. Okay, and it makes sense that it should be the sum of those two things because, well, all I did was take an area and carve it up into two pieces, compute the area of each piece independently, and then add up the answers. Right? That should work. Okay, so does that make sense? Okay, so what I would like you guys to do then is do B, C, and D on here. So 0 to 4, sorry, we just did 0 to 4. So do 4 to 6, 0 to 6, and 3 to 8. Okay? And while you're doing that, I'm going to grab some water. Okay, so what did we get for 0 to 6? 6. Okay, now why? Because, yeah, so the blue part and the purple part are exactly the same, but one of them is the negative of the other because it's below the axis. Okay, so it looks like 0 to 6 ought to be bigger than 0 to 4. Okay, 0 to 5 is bigger. Okay, so what's 0 to 5? That would be the green stuff plus the orange stuff plus the blue stuff, which you said was 7. Okay, but what happened when we added on the purple part? It canceled out the stuff that we had just added. Okay, so yeah, so this is all about net area, not total area. Okay, okay, do you guys buy that it's 6? No. All right, what about what was it? 4 to 6. Yeah, and we basically just said why, because the blue part equals the purple part, but one's above and one's below. Okay, and then finally from 3 to 8, okay, and there, let me pick another color. Okay, why is that the case? Well, what's the area? So 3 is here. Okay, so I've kind of split the orange part in half. And what's true about the right half of the orange? That has area 2. What about the red part? Has area 2 but counts as -2 because it's below the axis. Okay, and we already said that the blue and the purple parts cancel out. So what happens to this? And everything cancels perfectly, and so we just end up with 0. Okay, so it is totally possible to get 0 or negative numbers for these things. And the only thing you have to remember, particularly if you're using geometry formulas like we were here, is just, okay, if you computed the area of, say, that red triangle, you'd get 2, right? But then you have to remember, what does it really count as? -2 because it's below the axis. So just don't forget that last step. Okay. Now, when we do this for general functions, you don't have to actually do that much thinking because you're just going to end up plugging stuff into functions and get whatever you get. But if you're using the geometry, just don't forget that one extra step if it's below the axis. Okay. So does that kind of make sense? Okay. So um, let's do kind of the same thing here. For let's actually skip down to number 3. So number 2 is kind of the same idea, except it's a different function. But there is one thing about this I want to point out. What would the integral from 7 to 8 be of that function? Of the one at the top of the second page. Why? It's a straight line that's actually on the x-axis. So is any area enclosed? No, it's like a rectangle that has 0 height. Okay, so that also can totally happen. And it makes sense, right, if you just kind of use your head. Okay, so let's look at the number 3 here. Because here we don't have a picture, do we? No. Okay, so then what? Can we produce a picture? Yeah, we could. We could certainly graph it. What does, say, absolute value of x look like? Yeah, it's a v. Okay, but what's true about the absolute value if the values that we're dealing with are positive to begin with? Yeah, so absolute value of x, if x is between 0 and 2, the absolute value of x is just x, right? Yeah, okay. So this is actually the same as this. Okay, well, what is the slope of x from 0 to 2? The slope's 1, and so what's this area? Well, sorry. It's 2, right? Base times height over 2, just like before. Okay, and so we just get 2 there. Okay? All right. Now contrast that with part B, because what are we doing there? Yeah, it goes from -2 to 2. Okay, so the same trick I just did doesn't work here. Okay, but what does the graph look like of absolute value? It's that V shape, right? So if I go from -2 to 2, what do I get? Gotcha. Bazinga. Not 0. It's going to be 4. Okay. Why? Yeah, both pieces are above the axis for this particular function. And so I'd actually get 4 here because both triangles are the same shape, and we already knew that one of them had area too. Okay, so yeah, so even if the x's are negative, you can still have positive functions and therefore positive areas. The negatives occur when the thing goes below the x-axis. Okay, so you fool, you fell for one of the classic blunders. Yeah, okay. Okay, you guys know what that movie's from, right? Princess Bride? Mark. The princess is going to be the bride, but yes. Um, not technically. I forget who made it, but mhm, yes. My name is Inigo Montoya. You killed my father. Prepare to die. Okay. Um, okay. So let's do another one here. Let's look at. All right. So what does the graph of the sine look like? Yeah, it's a squiggly line, but not just any squiggly line. Right? So it's that thing, just repeated over and over again. And in this case, we're going from minus pi to pi. So even though we don't have any obvious geometry formula, because that curve is not like a semicircle or something we already know a formula for, uh, is it clear, though, that whatever the area of the positive piece is and whatever the area of the negative piece is are actually the same thing? Yeah, we don't know what either of them are individually, but we know that their sum is definitely 0. Okay. Now, later we'll talk about how we could figure out one of them individually, but that takes a little bit of extra work. Okay. Um, yeah, now this actually does kind of bring up a good point, which is just because it looks like the graph of one part and the graph of the other part are basically the same doesn't mean that that's actually true. Okay, if you just have some arbitrary function that may or may not actually work. Okay, but it is in fact true for the sine function, and the reason is that what is sine of negative x? It happens to be the same as negative sine of x. So let me write that down, what I mean. Okay, and if we think about, for example, your unit circle or whatever, right, then that identity is true. Um, and what does this mean about the sine function, by the way? What do we call such a function that has this property? That when you plug in a negative value of x, you get the same, or you get the negative of plugging in the positive version of that x. Anybody happen to remember? It's an odd function. Okay, so you guys remember even and odd functions from high school? No? No? Really? Oh, well, that's unfortunate. Okay, but sine does have this property, so we can do this, and we can verify this later when we know kind of the algebra for how to do that. Okay, so what about the last one there? We're going from -2 to 3 of 2x plus 2. All right, so what's the graph of this thing going to look like? Okay, it's a line with intercept 2 and slope 2. Okay, so we want the area between what? -2 and 3. Okay, so this is what I've got to look at, right? What's the area between this curve and the x-axis? Well, let me color it in. So I've got this piece, I've got this piece, and I've got this piece. All right, so what's it all total up to? So I'll take a little bit of mental arithmetic. All right, so well, let's just do it. So what's the orange part? 1, but it's actually negative, right? Because it's below. What's the green part? 1. And then what's the blue part? That one's a little bit harder. It's way bigger than that. So what shape is it? It's a trapezoid, okay? So the area formula for a trapezoid happens to be it's the base times the average of the heights. What are the two heights? The left-hand height is 2. The right-hand height, what do you get if you plug 3 into this function? 8. Okay, so this works out to be 15. What rectangle? You could do that, yes. So you could split it here into a rectangle that has area 6 and a triangle that's sitting on top of it. Ah, okay. Uh, okay. Yeah. So good point. So this rectangle, the stuff that's to the right of the orange but underneath the green, is not included in our computation because what are we looking for? We're looking for the area between the curve and the x-axis. Well, is that white rectangle between the curve and the x-axis? No, it's not. Okay, because what's between the curve and oh, I see. Guys, I'm sorry. I shaded in the wrong orange part. I should have shaded in above it. Sorry. Yeah, this is what I should have shaded in for the orange part. Yeah, my bad. Now it's geometrically the same, right? It's what I had shaded a minute ago. But yeah, this is what happens when your professor hasn't had coffee yet. Um, okay, so yeah, my bad. It's the stuff between the curve and the x-axis, and that rectangle that we were talking about is not between the curve and the x-axis. Okay, so it's just not important. Okay, then the other side on the trapezoid, you could always carve it up like I did here and say, okay, I'm going to think about it as this rectangular base with a triangle sitting on top of it and get the area that way. That's fine. Um, whichever way is easier to do it. Um, I've been told there's more than one way to skin a cat, so to speak. Um, Although somebody told me, who was I talking to? It was this weekend that you're not supposed to say that anymore because it's like cruelty to animals. Okay, so instead you should say there's more than one way to shampoo a cat. And I don't know about you guys, but I think most cats would rather be skinned than shampooed. So, yeah. Anyway, okay. So what's the total area then? 15, because it just so happened that the orange and the green parts sort of canceled out. Okay, that wasn't guaranteed, but that's the way it worked out. Okay, so does that kind of make sense? Yeah. All right, so let's look at maybe one more. It's not on the sheet, but I'll give it to you because it's fun. So the first problem with all of these is to figure out what shapes or what graphs are involved. Okay, square root of 1 minus x squared. Do you guys know what the graph of that is? Well, you could always plug it in, but it's what? Or almost, it's a semicircle. Okay. How do I know it's a semicircle? Well, okay. If I let y equals square root of 1 minus x squared and I square both sides and I move the x over, that looks like the equation of a circle to me. Okay. And the square root here, because I have the positive square root, that tells me it's the top half of the circle rather than the bottom half. Okay. So this is really a circle. And what is the radius of said circle? Radius, 1. Okay, what's the diameter? 2. This is what happens when the students haven't had coffee yet. Okay, so the radius is 1, and so the area is what? The area of the whole circle would be pi r squared, but we've only got the top half of it, so what is the area here? Just 1/2 pi, right? Because the radius happened to be 1. Okay, now let's say that it was something like this. Okay, so that I was going like there and I was computing this area. That's actually a much harder question. Okay, now you might sort of uh, naively guess, oh, well, maybe it's about half because I've kind of chopped the pizza in piece in half here, but is it exactly half? Not necessarily. Okay, and it turns out that answering this question is far more complicated than you might think it would be. Okay, so the fact in the previous one, the reason it worked out so nice is because we had an entire semicircle. Okay, but if I had done something like this, would this one have been easy? Why? That's a quarter of the circle, right? So it would be a quarter of the semicircle, and it's actually easy, right? So some of these can be deceptively harder than they might appear. Um, that just them's the breaks. Okay. Um, okay, and we'll kind of see why these things are some are easy and some are hard later. Okay. Okay. So um, let's move on to some properties of integrals here. Okay, so these are sort of generic properties that we're going to use a lot. Um, why do you think the following is the case? Hmm? Okay, yeah, it doesn't move, right? Well, if we're going from x equals a to x equals a, there's no area enclosed, right? It would just be like the width would be 0 and the height would be whatever the function is. Well, there's no area there, right? Does that make sense? Okay. All right. What about the second one? Why is this equal to this? Okay. This one's maybe a little hard to see geometrically. Um, but if you flip the bounds around, essentially what you're doing is you're moving from the right to the left instead of the left to the right, and you're going kind of backwards. Okay. And doing so is equivalent to just negating the function. Okay. So if you switch the bounds of the integral, you'll get the negative of the answer with the unswitched version. Okay. Now, there's good algebraic reason why that's true. Okay. For now, we kind of have to take the geometry sort of on faith, but we'll look at the algebra as to why that works, I guess, next time or the time after, right? But yeah, just take it on faith. If you switch the bounds, you negate the answer. Okay, now you'll notice actually in all of the examples that we've worked up until now, what was true about the bounds? It was always from lowest to highest. Okay, so we were sort of working from left to right with our bounds. the bottom bound was always the smaller of the two numbers, and the top bound was always the bigger of the two numbers. If that's not the case, you can always switch them at the expense of a minus sign. Okay. Right. Okay. Then this one we've used a whole bunch of times already, and you guys kind of said it was obvious. How did we use that identity up until here? Exactly, right? So if we wanted to go from say 0 to 6 of something, and you wanted to say, all right, I'll do 0 to 5 and 5 to 6 separately and then add up the answers, I'm talking about the same areas, so they should add up that way, right? So when we had the pictures, it was dead obvious that you could do that. And this is sort of the algebraic way of stating what we just did, that you could decompose the areas into multiple pieces, deal with each piece separately, and then add them up. Yes. Okay. Now, there's one caveat to this that was obvious in the graph case. What has to be true about the number C? It's got to be in between A and B. Okay. If it's not, then this doesn't really make sense. Um, but if it is, it does hold. Okay. And so, yes, you will be able to do that when you don't necessarily have a graph. But there, where the tricky part sometimes is choosing where C should, what C is, right? So when we were doing the pictures, for example, wasn't it obvious where to split things, right? Well, you split them where geometrically it just made sense to do so. Well, if you don't necessarily have a graph, then you can't just rely on that, okay? And so determining where a good split point is will require a little bit more finesse. Okay. Um, what about this? And actually, you know what? Let me back up a minute. Okay, so since several of you guys said that you'd never seen this before, let's say that you have a function, and it just so happens that when you plug in a negative x, you get so like you plug in -5, you get the negative of what you would have gotten if you had plugged in 5. Okay, now not every function is going to have this property, of course, but maybe some do. And it's functions that do have this property we call odd functions. Okay. Now, let's look at a couple of examples of such functions. Sine of x, it happens to be odd. But here are some other ones. Well, you use the definition. Okay, so I claim x cubed is odd, right? So I want to know what happens if I plug in negative x. Well, I would get negative x whole thing cubed. But what happens if I cube a negative? It's still negative, and that's negative f of x because f of x is x cubed, right? What do you mean the big functions? Oh, something that's big and nasty? Probably not. Okay. There's an exception maybe that perhaps you've noticed. Um, one of these, well, the x cubed I pick as polynomial. And what's true about its power? It's an odd number, right? Jade needs coffee. Okay. Yeah, the exponent is odd. Okay. So if you have a polynomial and every single power is odd, every single one, all of them, okay, then the resulting thing is in fact an odd function. Okay. And I suspect that this is actually where the name odd and even came from, because there are, if when you plug in a negative, if this negative just basically vaporizes, we call the function an even function, and x squared, x to the fourth, those are all examples of it. Cosine is one also. Um, yeah, so I suspect that that's why we actually call them odd and even in the first place, but I'm not for certain on that. But every single power has to be odd, or all of them have to be even. So if you have, for example, x squared plus x cubed, that one's neither odd nor even. Okay, it's in a different category. Okay, um, yeah. So there's a lot of functions that do satisfy this property, and you guys may have actually learned this in a different way. If you graph functions, what kind of symmetries can they have? It could be the case that they're symmetric about the y-axis, right? Those functions are even. And what about ones that are symmetric about the origin? Did you guys ever talk about that? Those are the ones that are odd. Okay, so this odd versus even thing kind of ties or corresponds to graphical symmetry of when you look at the graphs of the functions. So okay, anyway, um, if this is the case that you have an odd function, then the following is true. Then that equals zero. Okay, and the reason is because this area is this plus this. Okay, and those two things cancel out because the function this here is the same as the integral from 0 to a of f minus f of x dx, okay, by the property of being odd. And so what happens to the orange part and this other part, those are literally the same thing, just one of them has a minus sign in front of them. And so if you add those things up, then necessarily they're going to cancel. Okay, so if you have an odd function, and we have to be careful here, what's true about the numbers at the top and the bottom? They're the same, but one's negative. Okay, so maybe another way to put it is that this is defining an interval of x's where 0 is smack in the middle. Okay, it's symmetric about 0. If that's not true, then what we just wrote down doesn't work. Okay, so if it's lopsided to the right or to the left, it's not automatically going to be 0. Okay. Um, nope. Nope, not it wouldn't be. Nope. I mean, unless you pick the world's least interesting function, namely f of x equals 0. But that's not a particularly interesting one. So, yeah. Okay, so we'll continue with this stuff on Wednesday, I guess. And of course, don't forget you got the assessment today. If anybody's going to take it right now, give me about 10 minutes. I've still got to circle what everybody has to do on their paper, and then you guys can take them. See ya.